Let's talk briefly about the precise definition for the limit. That is, let's take a function f and let it be defined for all x values in an open interval containing a, but not necessarily defined at x equal a. Let's also let L be any real number. Then we say that the limit as x goes to a of f of x equals L, and we write it as such. If for every epsilon greater than 0, there exists a delta greater than 0, such that when the distance between x and a is smaller than delta, we have that the distance between f of x and L is smaller than epsilon. Let me dissect this definition a little bit and show you exactly what's being said. We start with a function, and that function is defined over an open interval on the x-axis. Specifically, that interval must contain a value a, but the function itself doesn't have to be defined at a. And so I'm going to denote that by drawing a function, and at a, I have this open circle because the function doesn't necessarily have to be defined there. Now, along with that, I'm going to define some value L and let that be a real number, and L is going to lie along the y-axis. Specifically, we're talking about L being the limit as the function goes to a. So L is going to be that y value that corresponds to a should it exist on the function. Sometimes it will and sometimes it won't exist. Now, what does it mean to be a limit? Well, the idea is this. We take any epsilon, positive number greater than 0, and we define around L an epsilon band, meaning we look at epsilon plus L and we look at epsilon minus L. L minus epsilon. And the idea is that the limit will exist if, when we look at the corresponding x values, we can find a delta band, a value a minus delta and a plus delta, such that all of the x values in that delta band around a will map correspondingly in the epsilon band around L. If that's true, then that means that all of these y values, all of the x values, are going to be mapping here in an area that's close or significantly close to L. Now, if we shrink that epsilon, because remember, we're allowing it to be any epsilon, so if we were to shrink that epsilon and pick a new epsilon value, specifically one that's smaller, and we were to take that epsilon band around L, so let's say epsilon is this distance here, and so L plus epsilon is the top notch, and L minus epsilon is the bottom, and we were to look at this band, again, we would correspondingly relate down and find a delta that corresponds to this epsilon to satisfy the condition. In this case, we would look and we would find that, okay, let's now choose a new epsilon. Let's now choose a new delta. So that I have all of the x values in this delta band around A now mapping to this new epsilon band on the y-axis. And if we continue that process for every epsilon, that's what gives us the idea of a limit, to where no matter how close we get to the L value, our f of x or y values will map infinitesimally close, as we approach A from both sides along the x-axis.